In this lesson, we'll talk about characteristics of a function called absolute extrema. Um, let's look at some examples in graphs. So here, this graph has endpoints, and the graph does not continue beyond that x value. If we look for the highest y value on the graph, that's going to be the absolute maximum. So this point has the highest y value, and we say the absolute maximum is whatever that y value is. It occurs at this x value. Here is a low point, but it's not the lowest point, so it's not the absolute minimum. The absolute minimum is here. So we have absolute maximum because it's above that. It's the highest point. Absolute minimum is there. Here we could say, well, there's a high point. But this graph goes on to positive infinity down to negative infinity. So this is not the highest point, and we wouldn't call it the absolute maximum. This is not the absolute minimum. It is a relative minimum. We'll talk about that in the next lesson. Here's a relative maximum. Over here, this is a relative maximum, but it's also the absolute maximum. This is a relative minimum, but this is the absolute minimum. And sometimes instead of absolute, they'll say global. Here, we're missing the endpoint. So when we look for highest and lowest points, we could say, well, there's a relative maximum, but it's not the absolute maximum because we have points over here. And this graph goes to infinity, so there's no absolute maximum. Here's a relative minimum. But the graph goes below that y value, so this is not the absolute minimum. And it never stops getting close to whatever y value is missing there. So that means there's no absolute minimum on this graph. So we have the highest or lowest, and the reason why this is called extrema is because the highest or lowest, those are extreme values. So the highest or lowest extreme values before we go on, let's think about how obvious this is to look at a graph and identify the highest and lowest point. But what we need to do is use calculus to find the highest or lowest point without looking at the graph. If we just have the function, how do we use the function to find a high or low point? So let's look at the absolute maximum. This absolute maximum occurs at a special point on the graph where the slope is 0. Here we have a slope of 0. It's not an absolute maximum. And the absolute minimum on this graph is at an endpoint. So we can look at an x value where the slope is 0, or look at an endpoint, and those are the 2 points where an absolute extremum can occur. Also look at this. Sometimes if this graph stopped here, we'd say that is the absolute minimum, and this angular part of the graph, the slope is undefined. So we would say we want to look for x values that have a slope of 0, an undefined slope, or look at an endpoint for the extreme values. Okay, so a function occur where f prime equals 0 or f prime is undefined. Or at end points. So now, without looking at a graph, we can just start analyzing the derivative. We want to see when is the derivative 0 or undefined, and then we also check the y values at the endpoints, and that reduces the possible locations of the extreme values. When we get a slope of 0 or an undefined slope, these are called critical numbers. Let's say the x values are critical numbers. And one more thing, one more concept or characteristic of absolute extrema. Usually you're asked to find absolute extrema on a closed interval where there are no arrows at the end. The function is only defined on a certain domain, or you're only given an x interval to look at. Here, this goes on, x goes to infinity, y goes to negative infinity, and so a lot of times they don't ask you about relative or absolute extrema with a graph like this, even though it's possible to have one. Usually the questions have a closed interval. Okay, so let's find the critical numbers. The critical numbers are when the derivative is 0 or undefined. So we have to find the derivative. The derivative of this is using the power rule, we get 2x. And then we want to know when the derivative is 0 or the derivative is undefined. So when is the derivative 0? It's when x equals 0. And it's never undefined because a polynomial is always defined. And then we just have to check the endpoints and maybe we should emphasize that this is f of x. So an endpoint from -1, endpoint's -1, the other endpoint is 2, and we'll also check the critical number 0, and we want to find the y values of the function. We're not using the derivative in this table. So we'll put a -1 there, and we get 2. Put a 0 there, and we get 1. Put a 2 there, and we get 5. So the highest y value is the absolute maximum. So that's this. The lowest y value is the lowest point on the graph on that interval. So let's see what that looks like if we have we have -1, 2, -1, 2, 0, 1, and 2, 5. So it's going to go like that. And we can see if we saw that graph, it would be obvious what the highest and lowest points are. Okay, pause the video and try that one. We do the derivative. We're using the power rule. We want to know when f prime is 0 and when f prime is undefined. So we have a critical number there with a polynomial. It's never undefined. 0, 1, and 3. The endpoints 0 and 3, and then the critical number. Find the y values, and let's emphasize that we're doing f of x. Put a 0 in here and we get a 0. Put a 1 and a 1, we'll have 2 minus 1. And then substitute a 3 and we'll get negative 3. So we'll have the lowest y value is the absolute minimum. It occurs at x equals 3. And then the highest y value is the absolute maximum. Zero, zero, 1, 1, and 3, negative 3. So we can see high point, absolute maximum, and the low point, absolute minimum. All right, pause the video and find the absolute extrema of this function on this interval. So to find critical numbers, we need the derivative, and that's going to be 6x squared, 18x plus 12. We want to know when f prime equals 0 and when f prime is undefined. It's a polynomial, so it's never undefined. And we could divide both sides by 6. And this is factorable. So we get negative 1 and negative 2. Two critical numbers. Let's find the highest and lowest y values. Negative 3 is an endpoint. 0 is an endpoint. And then we have critical numbers, negative 2, negative 1. Find all these y values. And when we substitute negative 3, we should get negative 30. No, negative 3. When we substitute negative 2, we get 2. And when we put a negative 1 in here, we get 1. And 0 is 6. So we look for the lowest y value, and that'll be the absolute minimum. Highest y value is the absolute maximum. And we could look at the graph. So at -3, we go to -3, -2, 2, -1, 1, 0, 6, and the graph might look like that. Since we're only looking for absolute extrema, it doesn't matter what's happening in here. We know that the absolute minimum occurs at the end point, absolute maximum occurs at the other end point. Alright, pause the video and try finding the absolute extrema for cosine on this interval. Critical numbers, let's find the derivative. Derivative of cosine is negative sine. And then we'll find out when f prime equals 0 or f prime undefined. When does negative sine x equals 0? When does sine equal 0? Divide by a negative. And we could think of it like this. When do we have a y value of 0 and a radius of 1? Y value of 0 is here and here. So that gives us 0 and pi. And negative sine x is never undefined. So we're going to look on this interval and also at these endpoints. 0 is an endpoint. It's also a critical number, so we just use one of them. Pi and 2 pi. So let's evaluate cosine at 0. That equals 1. Cosine at pi is -1. Cosine at 2 pi is 1. So we have it's a repeated absolute maximum. When we talk about an absolute maximum, it doesn't have to be a location on the graph, it's just the y value. So we see that the absolute max is 1, even though it occurs twice. And then when we look at the graph of cosine, we can see the absolute maxima there, and absolute minimum is there. And we'll stop there.